Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 2, A History of the Atom. Episode 8, The Electrical Atom. Before I begin into the narrative of this week's episode, I'd like to make a brief correction to something I said at the end of last week's episode. One of the things I did is I talked a little bit about a reference that I used in developing a lot of the material for our discussion of the periodic atom, including a book called The Periodic Table. In the podcast, I incorrectly pronounced the name of the book's author, Dr. Eric Sherry. Dr. Sherry is the author of a number of great books, including a book in the very short introduction series, which is really fantastic, and his latest work, a book titled The Seven Elements. I apologize for the error, and I hope you'll go out and take a look at Dr. Sherry's work. It's really quite good. So on to the episode. Theirs was a scientific collaboration that would change humanity's understanding of the nature of matter and chemical reactions, even if much of the chemical establishment at the time was either opposed to or didn't understand the new way of seeing how atoms combined to form molecules. Called the Ionians by Bernard Jaffe in his classic work Crucibles, which relates the history of chemistry through the lives of its most brilliant practitioners, Svante Arrhenius, Wilhelm Oswald, and Jacobus van Hoff reimagined the atom by looking to its electrical properties, and in doing so brought to fruition over 150 years of research. The investigation of electrical phenomena goes back at least as far as the pre-Socratic Greek philosophers and their study of the behavior of amber, and, as was the case in so many other areas of physical research, it received renewed interest in the Renaissance and afterward. It was English astronomer and physician William Gilbert who wrote the first comprehensive treatise on both electrical and magnetic phenomena in 1600, and it was in this work that the associated phenomena were first given the name electricity from the Greek word meaning like amber. Research continued through the 1700s, where more and more was discovered about electricity by a number of researchers, including one Benjamin Franklin, who established that all static discharges were one and the same phenomenon, though on vastly different scales. It was during this time that electric charge was first understood to come in two types, positive and negative. These researchers are what first drew Joseph Priestley into investigations of natural philosophy, and they were a source of much intellectual interest, though more so for those in the areas that would become physics than for those associated with chemistry. All of this would change, however, when an Italian natural philosopher, Alessandro Volta, would create the first constant current battery in 1800. Up until that time, electricity was stored in what was essentially a rudimentary capacitor known as a Leyden jar. While capable of storing electrical charge, Leyden jars were dangerous to work with as they would discharge with great energy through a person's body, and they had to be recharged after each single use, which was of rather short duration. What Volta did was to create a way of producing a relatively constant supply of electricity through stacking an alternating series of metal discs that were separated by a piece of salt water-soaked cardboard. Imagine each cell within the battery as a sort of sandwich, where the bottom piece of bread was a copper disc, the top piece of bread was a zinc disc, and the filling was the conducting cardboard. What Volta recognized was that this quote-unquote cell, as it was called, created a chemical reaction that produced electricity. If these cells, multiples of them, were stacked in what was called a voltaic pile or battery, the amount of electricity was multiplied by the number of cells in the stack. In this, Volta not only created a constant source of electricity, but he showed a relationship between chemical reactions and electricity. Now, before Volta had made this discovery, chemists had been using electricity to study various substances. What was already known by this time is that by passing a spark through water, the water could be disassociated into hydrogen and oxygen. What Volta's electrical pile allowed chemists to do was perform these sorts of disassociations in a controlled fashion with known amounts of electricity, even if what electricity wasn't really well understood at the time. Just as importantly, large electrical currents could be produced by building larger and larger batteries, thus allowing investigations of a number of different compounds. This would prove very important in the search for new elements, especially in the laboratories of two men, Jacob Berzelius and Humphrey Davy. Both Berzelius and Davy would use the battery to find new elements through the process of electrolysis, or the disassociation of compounds by passing electricity through them. Berzelius would discover silicon, selenium, thorium, and cerium, while Davy would isolate both sodium and potassium and show that they were different from each other and highly reactive. He also discovered calcium, magnesium, and boron and barium in this way. As important as these discoveries were, however, they would only be part of a larger legacy associated with what would become known as electrochemistry. Each man, working with his own class of substances, whether that be salts or acid, had found that not only did running a current through the compound lead to its separation, but that the component elements migrated towards one pole or the other. Think of it this way. Say you were to take a car battery with its positive and negative terminals and attach car jumper cables to those posts on the battery. In doing this, each cable becomes an extension of the post to which it is attached. The end of the cable attached to the positive post would now be positive, and the cable attached to the negative post would be negative. In scientific terms, the ends of the cables not attached to the battery are now called electrodes. So let's say you put each electrode into an unknown substance with the electrodes separated by a small distance. What you might see is that the substance would begin to change and separate in some way. One part of the substance would move towards the positive electrode, while the other would move towards the negative one. This is basically what both Berzelius and Davy did, but with batteries that had much higher voltage than that of a standard car battery. From this, Berzelius developed what he called his dualistic theory of chemical affinity. That said, quote, "In every chemical combination, there is a neutralization of opposite electricities, and this neutralization produces fire in the same way as it is produced in the discharges of the electric bottle, the electric pile, and lightning," unquote. In other words, what Berzelius is saying is that all compounds and elements, there's a part that's positive and there's a part that's negative. And when these parts are brought together through chemical reaction, they would produce electricity, and conversely, it required electricity to separate them. While this hypothesis would eventually be shown to be wrong, it provided a very useful idea to work from by associating electricity with parts of chemical compounds. As part of his work, Davy would make similar observations. Davy's contribution was to be more convoluted, however. In addition to his work in the area of disassociation, Davy was the beneficiary of a stroke of both good fortune and hard work. By the 1790s, it was realized that Britain had fallen behind the continental European countries in developing first-rate scientific institutions, both in terms of laboratories and teaching. While the country's reliance on the industry of its self-directed researchers and inventors had taken it far, it was becoming clear that the rise of scientific institutes in France, Germany, and Sweden were rapidly outpacing the contributions of the British. To deal with this, in part, The Royal Institution was chartered in 1799 as a place to both conduct first-rate scientific research in reasonably well-equipped laboratory facilities and to hold public lectures on scientific developments of the day. Davy was selected in 1801 to join the staff, and it was in this capacity that he performed the electrolysis experiments in the years 1800 to 1810, along with lecturing over a number of topics. Now, as a touchstone, in order to keep the present narrative anchored to our larger story, it's during this same time that Dalton was working in Manchester to develop his atomic theory. A topic, by the way, he would lecture over at the Royal Institution after being coached by Davy, who was, by all accounts, an excellent presenter. In 1812, Davy was injured in an attempt to synthesize a particularly explosive compound. In order to continue working while he recovered, Davy hired a young part-time assistant by the name of Michael Faraday. To say that this chain of events was fortuitous would be quite the understatement, as Faraday would turn out to be one of the most insightful and productive minds of the 19th century. I will save the full biography of Faraday's life for the series I'm planning on electricity and magnetism, but his was a story of humble determination and creative brilliance overcoming poverty and prejudice to set the foundations of our modern world. Working first with Davy and then independently, Faraday was able to better understand the nature of electrolysis, and he arrived at two laws that governed its behavior. The first of these laws stated that the mass of the substance altered at an electrode was proportional to the amount of electricity transferred at that electrode. The second law said that for a given amount of electricity transferred, the mass of the substance altered was directly proportional to the substance's atomic mass divided by its charge. The upshot of these two laws of electrolysis was to show that electricity acted as a chemical reagent that takes part in chemical reactions in specific proportions. From this, Faraday was able to conclude that electrolysis occurred when electricity flowed through a solution, or a substance, creating electrically charged fragments he called ions. These ions could be either positively or negatively charged, and would be attracted to the oppositely charged electrode, causing them to carry an electric current. In order to clearly distinguish between different charges, he called the positively charged ions anions, while the negatively charged ions were called cations. The electrodes were similarly named, with the positive one being the anode and the negative one being called the cathode. Published in 1832, this work would form the foundation of a new subdiscipline of chemistry known as electrochemistry. In conclusion to my discussion of Faraday's contributions here, I would like to note that this work was only one part of Faraday's contribution to not only physics and chemistry, but also a number of other applications of a more industrial nature. As I said before, we'll return to take up Faraday's work in electromagnetism in a future series of podcasts. This brings us to the three men I mentioned at the beginning of the episode. Following Jaffe's account in Crucibles, let's begin with the man whose ideas will form the foundation and central aspect of the narrative, Svante Arrhenius. Arrhenius was a chemist brought up in the rich Swedish tradition of chemical sciences, dating all the way back to Schelle through Berzelius, Linnaeus, and Malspender. A wunderkind, Arrhenius moved quickly through the Swedish education system until he reached the university level, where his unorthodox ideas regarding chemistry would begin to create difficulty for him. For his PhD dissertation topic, Arrhenius had decided to tackle a difficult problem that dated back to Faraday. The fundamental issue of the problem was that no one really knew what was going on when an electric current passed through a solution in low enough quantity so as to not induce electrolysis. This issue had laid somewhat dormant between the time of Faraday and Arrhenius because there were either more fundamental issues, such as dealing with the apparent discrepancies of Dalton's atomic theory and the work of Gay-Lussac, or there were easier problems to work on, as was the case in the new and fertile field of research in organic chemistry. However, After the Karlsruhe Conference in 1860 and the creation of the periodic table by 1872, electrochemistry had once again returned to the fore as a preeminent research problem. What was known was that it was impossible to pass an electric current through distilled water. However, if one added just the slightest amount of salt to the water, the resultant solution was able to allow for the passage of current from one electrode to the other with little resistance. Additionally, it was noticed that a decomposition of the salt would take place. Arrhenius set out to understand what was happening in adding salt to the water. His research initially followed the lines similar to those pursued by Cavendish a century earlier, in looking at how the concentration of different salts affected the conductivity of the solution. While Cavendish had passed the current through his body as a way to measure its strength, a method both startling in its peril and surprisingly accurate, Arrhenius used the tools provided by Faraday's work on electromagnetism, including a current measuring instrument called a galvanometer, to measure that amount of electricity flowing through the solution with very great accuracy. What he found was that the key lay in investigating solutions where the concentration of the salt was very, very low, much lower than had been previously investigated. It turned out that low concentration solutions of salts and acids were actually better at conducting electricity than high concentration solutions were. In 1883, he hit upon a new hypothesis of electrical conductivity that modified the work of Faraday. His idea was that when a salt was dissolved in water, the component elements became disassociated from each other, free to move independently in the solution. These fragment elements, however, were not electrically neutral, but instead carried a charge with them, either positive or negative. Whereas Faraday's hypothesis was that the passage of electricity created the ions, Arrhenius said that the ions were formed as soon as the salt dissolved in the water. Through the dissolving, there were no more salt molecules in the solution, but rather only ions made of the two constituent elements. The best example to illustrate this is that of common table salt. Known in chemical terms as sodium chloride, the table salt, when dissolved, would completely dissociate into positive sodium ions and negative chloride ions. Moreover, the ions would have different chemical properties than the elements they were formed from. Chloride, rather than being the toxic gas chlorine was, would remain in the solution. The same would be the case for the sodium ions, which, had they retained their elemental properties, would have reacted explosively with the water. When an electric current was run through the water-salt solution, the ions would travel to the oppositely charged electrodes, where, upon contact, they would give up their charge and return to their elemental state, sodium collecting on its electrode and chlorine gas bubbling off the other. This was a fairly radical idea, and it wasn't well received by the chemical establishment in Sweden. Arrhenius was savvy enough to understand that if he presented his entire hypothesis as part of his dissertation, he was likely to be denied his doctorate. So his presentation focused on the data he collected and the relationships he was able to deduce from that data, with the idea of ions only being hinted at. Nevertheless, while he did earn his degree, it was awarded at only the third rate, a bitter pill to swallow after all his hard work. Nevertheless, with his degree in hand, Arrhenius began to look for places that might be more receptive to his ideas in order to do his work as a postdoctoral fellow. He sent his dissertation to a number of places only to be ignored or just faintly encouraged, at least until finally Wilhelm Oswald read it. Oswald was a highly energetic professor of chemistry in what was known as the Polytechnical School in Riga, in what is now Latvia, but at the time was part of the Russian Empire. Oswald was known for championing all sorts of innovative ideas in chemistry, and he immediately saw the genius of the idea of ion formation in solutions. Oswald quickly decided that it was worth fighting to see that the hypothesis was disseminated as widely as possible, with as much experimental support as possible. So, he first traveled to Stockholm to meet with Arrhenius and discuss the young chemist's ideas more fully. Recognizing that the chemical establishment would take a great deal of convincing before they would accept them, Oswald began to plan how to provide evidence in support of these ideas. He invited Arrhenius to take a fellowship at his institution in Riga, but at that moment, Arrhenius' father passed away, necessitating a delay. In due time, however, the traveling fellowship was granted, and Arrhenius joined Oswald in Riga. Oswald was working at the time on the conductivity of acids, and the two men joined their researches under the same impetus of investigation. In 1886, a German chemist in Würzburg, one Friedrich Kohlrausch, published work showing that the ions of a given element, no matter which compound they came from, behaved in exactly the same way, indicating that the ionic properties of a given substance were associated with some physical property of the elements they were formed from. Arrhenius traveled for a time to Würzburg and worked with Kohlrausch and a young organic chemist by the name of Fischer. In Kohlrausch's lab, Arrhenius rededicated himself to collecting a mountain of evidence to support his hypothesis. It was also during this time that Fischer introduced him to the work of the Dutch chemist Jacobus Heinrich van Hoff. Van Hoff was already a well-known chemist, specifically for his work in organic chemistry. He had pioneered the idea that some molecules would have three-dimensional structure and that such structure would affect the chemical behavior of the molecules in profound ways. This idea gave rise to what is called stereochemistry and quickly became a foundational idea in understanding the structure of complex molecules both within and outside of organic chemistry. Of course, not everyone had been in favor of such a radical rewriting of how molecules were arranged, and some likened stereochemistry to witchcraft. Nevertheless, Van Hoff fought his way through such opposition, and in doing so, had gained a bit of a reputation as a maverick. What was more accurate was that Van Hoff had the rare ability, like Arrhenius and Oswald, to see beyond the present boundaries of his discipline and look for new explanations. He also understood how to get controversial ideas accepted by the scientific mainstream. Now, Arrhenius had heard about Van Hoff through a paper the latter had written about how substances dissolved in solutions seemed to obey many of the same laws that gases did in diffusing through each other. In the paper, Arrhenius found experimental evidence that would support his ionic hypothesis and bring his various ideas into one unified whole. In 1887, after stops in Graz to meet with the physicist Ludwig Boltzmann and Kiel to talk with Max Planck, Arrhenius made his way to Amsterdam to meet with and work with Van Hoff. Immediately, the two men developed a strong friendship and worked unselfishly to find evidence to support each of their own ideas as well as the ideas of the other. It was a relationship that would last until Van Hoff's death in 1911. After several months of work, Arrhenius had acquired enough evidence that he felt he could put forward his full theory. During this time, Oswald had been appointed the professor of chemistry at the more prestigious University of Leipzig, and he once again invited Arrhenius to join his growing research team there. One of the things Oswald had done upon arriving in Leipzig was to found a new chemical journal, and I'm probably going to butcher this, but the journal was called Zeitschrift von Physikalische Chemie, or more in English, the Journal of Physical Chemistry. The purpose of this journal was to allow for the freer publication of work that was often blocked by the old guard of chemists who were somewhat antagonistic to the more theoretical approaches being developed in several fields that would be gathered under the umbrella of physical chemistry, and that included electrical chemistry or electrochemistry. The two men, in concert with Van Hoff, pulled together the entire edifice of Arrhenius' ideas of ionic behavior and began to publish them, being sure to support the more theoretical ideas with experimental evidence that they had acquired over the last 5 years. Oswald's campaign of publication spread both the theory and means of investigation throughout Europe. Additionally, as students came into his dynamic research team, they learned the ideas of ionic theory, which they then took with them to other appointments. While not every one of these students supported the ideas being developed, they all participated in the ongoing research surrounding the topic, as did their students when they moved on. In these ways, Oswald was able to force a discussion of the merits of the scientific theory of ions into the universities of not only Europe, but also the growing chemical community in the United States. Jaffe calls Oswald's research group, led by him, Arrhenius, and Van Hoff, the Ionians, and compares them to a small army going off to do battle with the forces of chemical inertia found in the established academies across the continent of Europe. While this is just a bit of dramatic license, it does capture the spirit of the three men and their students who sought to get a fair hearing of their ideas beginning in 1887. Over the next several years, Oswald's group would put forward their work in the pages of Zeitschrift, working hard to support their theory with evidence arrived at in the laboratory. The opposition had hung their criticism on the charge that Arrhenius's ideas were mere theoretical conjectures, more suited to the ramblings of philosophy than the chemical bench and crucible, and so Oswald focused on providing the hard empirical evidence needed to counter such claims. His group at Leipzig attracted students from all over the world, especially England and the United States, and, for a time, it was the beating heart of physical chemistry. Within 3 years, the three men were invited to present their ideas to the British Association for the Advancement of Science, a coup as it meant that their ideas were being taken seriously. Scientific opinion had moved from being in opposition to being split among three groups. There were those who supported the theory, those who opposed it, and, in a display of humility, those who admitted to not being competent enough to be able to pass judgment on it. In this environment, the three Ionians, to use Jaffe's label, were given an opportunity to present their ideas and answer the questions of the best and brightest chemists in Britain. While the meeting didn't win everyone in attendance over, especially many French chemists, it marked a new level of acceptance, and the three men left England with a renewed sense of energy and vision with which to continue their researches. It is at this point that I'd like to take a brief digression. In the episode on the first chemical revolution, I mentioned that the dissemination of scientific research and ideas was often a slow and laborious process. As such, some discoveries were made nearly simultaneously by several researchers, as was the case with oxygen. The downside of this, of course, was that oftentimes information that might have sped along a line of research in an area was often neglected or missed. This was the case with the explanations of Avogadro, which had to wait 50 years before Canizzaro's reformulation introduced the larger chemical community to their benefits. In almost all of these cases, the various revolutions and wars in Europe, beginning with the French Revolution and the resulting Napoleonic Wars, up through the revolutions of 1848 and through the wars of German and Italian unification, served to impede scientific progress in the field of chemistry. However, following the end of the Napoleonic Wars, with the previously mentioned interruptions noted, Europe entered a century of long relative peace and stability. During this time, the ability of scientists to share their ideas and build upon the work of others led to the dramatic advances in many areas, including chemistry. While it has been rightly said that war can drive great technological innovation, it seems clear to me that it serves to hinder fundamental scientific research by cutting off the collaboration so necessary for the rapid development and evaluation of ideas. As we will discuss in the episodes to come, the period from 1870 to 1914 is marked by an unprecedented expansion in our understanding of the nature of matter. Returning to the narrative at hand, however, As the three men continued to press their case, they began to win converts who started to research programs of their own. Perhaps the most influential of these was a Swiss chemist by the name of Alfred Werner. Beginning in 1893, Werner's research focused on the idea of how the ions formed in solution, and from it he developed a comprehensive theory of ion formation. In this theory, he showed that metals form ions in actually two different ways. The first, which was the stronger of the two, he called ionic linkage, while the second he called non-ionic, now known as covalent linkage. This work would directly prefigure modern bonding theory and would provide answers to a number of questions surrounding Arrhenius' ideas regarding complex molecules involving more than two types of elements. Over the next few years, the evidence in support of the ionic theory of Arrhenius would overwhelm the opposition marshaled against it. In 1895, Arrhenius was finally awarded a professorship in Sweden for his work, and within 2 years was promoted to the rectorship or presidency of Stockholm University. All three men traveled to the St. Louis Exposition in 1905, and before the end of the decade, all three men would be awarded the Nobel Prize in Chemistry for their work. In the meantime, however, a British physicist had made a discovery that would not only explain what ionization was and how it took place, but that would fundamentally alter the picture of the atom of Dalton. In 1899, J.J. Thomson announced the discovery of the electron and ended the idea of an indivisible atom. Before we get to that, though, we need to take one final excursion into developments during the 19th century that supported the existence of the atom through investigations in heat, statistical mechanics, and electromagnetism. Thus, in our next episode, we'll look at the physical atom. Until then, full sails.